All right, welcome back. We're going to go ahead and talk about piecewise defined functions. So talk about just a couple of examples. Always it's good to start with an example first. So one example is the absolute value function. Let's take y equals the absolute value of x. Now you can actually write this, we've talked about it before, as the square root of x squared. But another way to think about this is you can think about this as having two separate definitions. Okay. Two separate definitions dependent on where you are on what your x values are. Okay. This could be x if x is greater than or equal to 0, and negative x if x is less than 0. Okay, so let's just see how that graph looks like. Okay, one thing, since we're talking about increasing and decreasing, I just want to make sure we understand this is actually decreasing as you move from left to right over in this area. So let me just real quick, not really what we want to talk about, but just so that we know, decreasing on negative infinity to 0 and increasing from 0 to infinity. Okay, so now what I want you to notice is that we have defined it separately dependent on where we are for x values. Okay, so that's really the point. So x, if x is greater than or equal to 0, so let's say x is 1, then y is 1, right? Here, negative x, if x is less than 0. So if x is negative 1, then y is actually going to equal 1, right? The negative of negative 1, okay? Another piecewise defined function that we talk about in this class is what's called the greatest integer function. Okay, we don't talk about it much, but it does show up in the homework. And that is y equals, got this funky brackets on it. And I like to remember it that we're rounding down. Okay, so the greatest integer of 1.3 is going to equal 1. Greatest integer of 1.9 equals 1. Greatest integer of 2, that equals 2 now. Okay, so if we wanted to graph this thing, starting to get an idea of what it's supposed to look like. Okay. So then at 1, between 0 and 1, it's actually going to be 0. But then at 1, it bounces up here to 1. Between 1 and 2, it's going to be 1. And then at 2, it bounces up here to 2. Keeps going like that forever. And goes in the same way on the left. Okay, so now, what would be, for example, a question? Well, I might ask you, what is the greatest integer of negative 2.1? Okay, so since you've drawn this picture, negative 2.1 is here. So what would that be? That's actually going to be negative 2. Hold on, let me just make sure of that. Negative 2. Nope, I screwed it up. Not badly, but I've almost made the mistake I don't want you to make. Negative 2.1 is here. So what's the greatest integer of negative 2.1? actually -3. Okay, all right. Another question that I see in the homework is we give a couple of lines here. Okay, gonna have the point 3, 8 here, the point 5, 2 here, and then the point 10, 1 here. Okay. Okay, we want to find the expression here. So find an expression, find a piecewise expression for this function. So even though it has two pieces, still a perfectly fine function, okay? And we can find the expression for it. So now what we're going to have to do, though, is we're going to have to find the equation of a couple lines. So we're getting back into 1.2. So equation of line connecting 3, 8 and 5, 2. Well, our slope is going to be 2 minus 8 is -6. 5 minus 3 is 2, so that's -3. I want you to notice something. This decreases, and so you have a negative slope, so that makes sense. Okay. Find the equation of that line. That's going to be, we're going to take y equals -3x plus b. We're going to use either one of these points. Let's use 3, 8. So 8 equals -3 times 3 plus b. 17 equals b. So our first line is y equals -3x plus 17. I'm looking, and that actually looks reasonable. I can reason that it will cross up here at 17. Okay? Now let's find the equation of the line connecting 5, 2, and 10, 1. Okay, so doing the exact same thing. My slope is going to be from 1 to 2 is -1, from 10 to 1 is 5. Again, as you move from left to right, it's decreasing. So a negative slope makes sense. Y equals -1/5 x plus b. Let's use the point 5, 2. So 2 equals -1/5 times 5 plus b. 2 equals -1 plus b. B equals 3. So this line is going to be, y equals -1/5 x plus 3. Okay, so we've got two lines here. Now, how are we going to join them together to make this a piecewise defined function? Well, there's a break point. There's a break here when x equals 5. In this case, we can actually use either one. Okay, we can use either one to define the function at 5. So what we can say is that y equals negative 3x plus 17 if, now this is between 3 and 5. So 3 is less than or equal to x. Now I can write either less than or equal to. Let's put less than or equal to 5. And then I'm going to write y equals the other equation, negative 1/5 x plus 3 if, now here at 5, I'm not going to include it, okay? It's just the way that we do it. It's part of the whole thing of like a function can only have one value at an expression. Technically, I guess we probably could include the 5 there since they're both doing this, giving the same output at 5. But we just, as a practice, we don't put that down there. So between 5 and 10. Okay. All right. That's it for 1.4. I'll see you guys in the 1.5 section.